It's Musai here, and we're doing a video this time on how to approximate the binomial distribution to a normal distribution. Now, as we know, the binomial distribution is a type of discrete probability distribution, whereas the normal distribution is a type of continuous probability distribution. So suppose we have a random variable x which follows a binomial distribution whose parameters are n and p, where p is the probability of a success and n is the number of observations or the number of trials. And so suppose that x follows this binomial and there are 750 trials and the probability of a success is 0.25. Now, if we were supposed to calculate p of x greater than 200, then that would require us to calculate p of x equal to 201 plus p of x equal to 202 plus several thousand years later p of x equal to 750. This will take a very long time to do, and we don't like to waste time. But since n is large, what we can do, we can approximate the binomial distribution to a normal distribution. So to do that, we would say the mean, which is the expectation of x for a binomial, is equal to n times p, which in this case is 750 times 0.25, which equals to 187.5, and the variance of x, which is equal to sigma squared, is equal to n times p times q, which is equal to 750 times 0.25 times 1 minus 0.25, and this equals to 140.625. Now, the parameters for normal distribution is the mean and the standard deviation. So the standard deviation is equal to the square root of the variance, which is equal to the square root of 140.625, and this is equal to 11.8585. We have x, which is approximately equal to a random variable y, where y follows a normal distribution whose mean is 187.5 and whose variance, whose standard deviation is equal to 11.8585. Now, if you want to calculate p of x greater than 200, then that is equal to p of y greater than or equal to 200.5. So you might be asking why there is a 0.5 there. Well, that is because of continuity correction, because we're moving from a discrete random variable, x is a discrete random variable, to y, which is a continuous random variable. And to move from a discrete probability distribution to a continuous probability distribution, we must apply continuity correction. Within every value for the discrete random variable, there are gaps in between, and in a continuous random variable, there's no gaps in between. Therefore, to account for these gaps, we must apply continuity correction. Now that we have this p of y greater than 200.5, we must now standardize it. So we must calculate the z-score. P of z greater than or equal to 200.5 minus the mean, which is 187.5, all divided by standard deviation, which is 11.8585. Now, in case you don't know where I got this formula from, just recall the z-score is equal to x minus mu over sigma. But in this case, our variable is not x, it is y, but the same formula holds. So this is equal to p of z, and when you work this out, it should get 1.10. Now, I approximate this to two significant figures because my standard normal table has 2 decimal places alone. If, however, I had an Excel document or some other computer software that will allow me to use more decimal places, then I would, right? other mathematicians sometimes interpolate between two numbers to get a more accurate answer. So what we can do now is that we can sketch a general normal curve. Here should be 0. No, it should be symmetric. I apologize for my bad drawing skills. And here along here should be 1.10. So we know that, so we want to calculate the probability of z greater than 1.10, which is this shaded area here. Luckily, that's the exact area that my standard normal curve gives. I just need to look for 1.1 within the standard normal table in order to find the answer. So this is the standard normal table, and I just need to look for 1.1 within the standard normal table, and I'll get the answer. So 1.1, which is here, which is 0.1357. 0.1357, and that's the answer for this question. 0.1357 or 13.57%. That's the probability of P of X greater than 200. Hi everyone, it's Musai here, and you have just completed watching my video on how to convert from a binomial distribution to a normal distribution. So if that video helped you in any way or you enjoyed it, please make sure to like the video and subscribe to my channel, and it will be really appreciated. Thank you very much.